This is a recording for Edexcel Further Pure 1. Inequalities section 1.1, solving algebraic inequalities involving polynomials. Well, you should already be able to solve quadratic inequalities such as this one, x squared minus 3x minus 4 is greater than 0. And we can do this by factorizing and finding what are called the critical values. Now the critical values here would be at x is equal to -1 and x is equal to +4. So these are the values for which the function f of x is going to turn from positive to negative or vice versa. So we can mark those on a graph. X is equal to -1, x is equal to +4, and because this is a positive quadratic, so we've got positive x squared, we know that it will be the standard parabolic shape. It will come down through -1, cross the y-axis, and then go back up again through +4. So just marking those critical values on my graph. And from that then we can see that the region for which the graph is above the x-axis, so where f of x is greater than 0, will be those values which are below -1 and those values which are greater than +4. Now we need to use set notation with Further Pure 1, so this would be the set of values x such that x is less than -1, union with or the set of values that x is greater than +4. So it's this method of finding critical values and then deciding the regions for which the function is positive or negative that we're going to use for higher order polynomials. So here is such a higher order polynomial. This happens to be a quartic, so we've got x to the power 4 as our highest power, and we start off by finding the critical values. Well, here the polynomial has been factorized. If it isn't, then you could factorize the polynomial first, and we can see here that our critical values where x is equal to 0, or I beg your pardon, the function is equal to 0, would be x equal to 0, x equal to +1, and x equal to -2. Now we don't necessarily need to draw a graph. We can actually do this inequality by using a table of values where we use the critical values to show the regions for the function. Let's do that on the next slide. So here we can see on the top line of the table we have the regions which are separated by those critical values. So x equal to -2 would be here, x equal to 0, and x equal to 1 would be the lines, if you like. Now for the regions of the graph, we can then decide whether each of these factors is positive or negative. Now in this particular case we have got one factor which is squared, so all of those we could immediately mark in as being positive. For any region of the graph, a factor squared must be positive. If we look at the other two factors, then when x is less than -2, they are both negative. As we move then into the region -2 to 0, then the first of those factors at the top, x plus 2, will turn positive, but x itself is still negative. Then when we cross into the next region between 0 and 1, well, this one will be positive, but x also turns positive. And of course, above x equal to 1, so x greater than 1, all of the factors are positive. We can then combine those to work out whether f of x is positive or negative. So in the first column, we've got two negative factors and a positive, so in total that is positive. It then turns negative, and then finally 2 regions which are positive. So the region that we want, the less than or equal to here, the region that we want must be given by this one here, -2 up to 0. But remember that our inequality is less than or equal to 0. So we must include the endpoints. Then we would have x such that -2 is less than or equal to x is less than or equal to 0. Now looking at the final line there, you might think, well, that's our full solution, but remember that we've got less than or equal to, so we must consider those critical values carefully, and there's one other value where x is equal to 1, which will give us 0 for the function. So we must also have union with the set of values x such that x is equal to 1. Now with polynomials like this, it is also possible to sketch a graph quite straightforwardly, so I'll consider that on the next graph, and it might be a little bit clearer why we get these particular solutions. Well, to sketch the graph, we can mark on our critical values on the x-axis, so they're at -2, at 0 and +1. This is a quartic graph, so it would start off in the positive region of the y values, cross at -2, and then reach some minimum value before coming back up through 0 into the positive region. +1 is quite an interesting point because we have here what's called a repeated root. It's that x minus 1 all squared, and that is a point at which the graph will just touch the x-axis rather than crossing it. So it goes in this sort of fashion, touching the x-axis and then back into the positive region. So the graph then allows us to see rather more easily where we have less than or equal to 0. And we can see that that will be between -2 and 0, and include those values -2 and 0, and also the point at +1. So I've got that on a nice neat graph section. So there we are, the values from -2 up to 0, including those critical values -2 and 0, and also that single point x is equal to 1. So to reiterate then, solving higher order polynomial inequalities involves finding the critical values. We don't necessarily need to sketch a graph. We can do it by tabulating and then calculating whether the function is positive or negative. But remember, when you have inequalities such as less than or equal to or greater than or equal to, it's very important to check carefully those critical values. That's the end of this particular video. In the next one, we will look at inequalities involving algebraic fractions.